Good evening and welcome to this training workshop on NetworkX, a Python library for network analysis. So here we have Dr. Sharad Babu, who is a research scientist in the Center for Wireless Communications and Innovation of Department of Electrical and Computer Engineering, Iowa State University, who has been an expert in Python uh, uh, and he graduated from IIST as a PhD uh, uh, yeah, scholar 2 years back. And he has conducted several such workshops and conferences for IEEE and other organizations uh, in relation to Python as well as wireless mesh network and so on. So with this let me introduce this class. So, Dr. Sharath, this class is about the complex networks. So this is an elective course for BTech 7th semester and MTech students. So we have about 22 students here who will be learning from this workshop. So yeah, with this introduction, let me invite Dr. Sharad Babu to start the session. Thank you.
Yeah. Yeah. Hi, everyone. Actually, happy Teachers' Day, sir. Today is Teachers' Day. So,
Thank you. Thank you.
um, so today I will try to give an introduction to NetworkX. It's actually a very simple Python library for network analysis, and it's a big library. But I just want to give you an introduction because I cannot cover everything in 1 hour. But we will try to see whatever required for you probably, because I did some of my work in PhD with this NetworkX, and it's very easy to use given that if you know Python, basics of Python, that's more than enough to do this NetworkX. So I think you have a brief idea of graph theory, nodes, edges, weights, and all those stuff. Then it's easy. I provide you the material probably after this talk, so that if you want to take notes, it's okay. You can take. I will just go through the main features of this library, how to create a basic graph, and how to do some simple analysis. And if you are actually doing some analysis from a data set that is downloaded from some repository, then how you can load the data and create the graphs, networks from that data set, from the file, and all those stuff. Just how to draw the graph and many very minimal stuff, just as an introduction, so that you can learn from that. So I have only one slide to show you. Remaining, maybe I can code and show you how things are. So NetworkX is one of the popular libraries for graph theory and network analysis in Python. It's one of them, but we have many. You can do everything with matrices and all, but the in programming you have object oriented concepts. So if you do some programming with object oriented concepts, it's very easy to visualize the things and see it in a real fashion and do the coding. So NetworkX is one of the library that is primarily made up of these object oriented concepts, and it's purely developed in Python. And its original developers were actually Eric, Peter, and Dan. They are from Los Alamos Laboratory, USA. So they are mathematicians, and they developed this. And its latest stable release is kind of 2.8.6. One of the thing is that this NetworkX went through different versions. Usually, there are some problems with. It's not problem. It's actually some behavior of Python library versions. Some of the new versions will not be backward compatible with previous versions. So you can always try to use the latest version. So this is the latest stable version, that is 2.8.6. Then its source code is available in GitHub. So it's an open source thing. So you can just download. You can see, you can modify the code for each algorithm and all those stuff. So this is the web page. If you go to the web page, you can see a graph here, and their documentation, stable release, and all those stuff, some features. Then documentation can be downloaded from as a PDF. That's also available. Then this is one of the major thing that I want to emphasize. You can get everything from here. This is tutorial. So if you go to their tutorial, you can see all the features that are available in NetworkX. Basics, how to create graph, then reporting algorithms, and all the stuff. So how to these are of interest for you, these algorithms. So if you go to a particular, for example, centrality, right, you can see what are the functions that are available in finding out the centrality measures. Maybe you are familiar with centrality measures now, the closeness centrality, then betweenness centrality, all those functions. And if you go to the function, you can see the complete details, means even which algorithm they implemented, and even references to that particular papers also. So it's a very well documented library. So this is very useful for you, this tutorial. Then as I told, the prerequisites for this is basic knowledge in Python. That's more than enough. You need to be very familiar with the list and dictionary data structures, because many of the functions and the features are implemented using dictionary. So dictionary is a very important data structure. It's an efficient, time efficient data structure in Python. So you should be very familiar with the list and dictionary. Tuple is okay. It's even if it is not familiar to you, it's okay. But list and dictionary you need to be familiar with. Then object-oriented programming is a plus actually, because all the objects, graphs, not functions, but mainly graphs and graphs related structures are actually implemented using object-oriented concepts. So that's about NetworkX. And if you want to try a different library, there is another one called iGraph. I also used iGraph a lot. Why? Because iGraph is developed in C++. So if you analyze complex graphs, sometimes it may take a lot of time. So the implementation matters, right? Implementation, the language primarily influence the running time. So iGraph is a bit more faster compared to NetworkX, but it's okay. But people are nowadays using NetworkX. iGraph is also can be used. iGraph is having its own features, but it's almost similar. So that's about the NetworkX and the library. So any questions? If you have any questions, just stop me and just ask. So any questions from this?
Anybody, any questions?
No, sir.
Okay. So probably we can go to the code. So I just open the Jupyter notebook. This is a Python interface for doing Python programming. So I want to mention you that apart from uh, basic Python, you need to install two libraries, mainly two libraries for doing some coding in NetworkX. One is, of course, the NetworkX library, and another is matplotlib. It is for plotting. So if you want to see the graphs, you want to plot the graph, right, as a figure or something. Mainly, it is doing it's plotting using matplotlib. So we need to install two libraries, NetworkX and matplotlib. So these, if you are doing in Linux, then you can install it like this. Maybe let me do source. Yeah, this is the command to install NetworkX and matplotlib. So if you do NetworkX, it's already installed. That's why it is showing the requirement is already satisfied. So the next thing is matplotlib. That's also installed. So requirement already satisfied. Otherwise, it will just show it will install the NetworkX and matplotlib. So these are the two libraries. Nothing else is required for doing Python, doing NetworkX. So let's go. So first what we need to do is I will show you how to create a node and an edge or something using a simple NetworkX. So first thing that you need to do is in Python, you need to import the NetworkX library. So this is I just imported the NetworkX. Sir, my screen is visible, right? It's readable.
Yes, it is visible. Yes.
Okay. So this is the way to import the library. So NetworkX I just imported. So I just gave an alias name for NetworkX. So it's like import NetworkX as NX. So I can use NX for the future reference for this library. So this is the way how to import the library. Then creating graph is very simple. So just create a variable. So nx.graph. Yeah, now you created a graph. Okay, that's all. So with 2 lines, you can create a graph. So you can see that how simple it is. Now I created a graph, and if I print the graph, so this will create a graph, and it will give to a variable g. So if I print, just run this, you can see that what will happen. So no, is it working with the complex network? Okay. Oh, let me see. I will put it in. Yeah, so you can see that when I run this, it will this statement print a graph with 0 nodes and 0 edges. Means I just created a dump graph, right? It's not having any nodes or edges. So if you want to add a node, what you need to do is just there's a function called add node. So I can add a node, maybe 0. So it will add a node with a node. Its value is 0. The node will be 0. Then I can add a node with a string also. There is no problem. You can name the node with anything, with an integer, with a string, or whatever it is. There is no issue. So now if I run, if I just print the graph, you can see that, yeah, graph with 2 nodes and 0 edges, right? It is having 2 nodes, right? 0 and a. So then now we need one more thing, right? The link to make it a graph that you want to see. So maybe you can guess what will be the function to add the link. So what can be? It should be add link, right? Or add edge. It's actually edge. Add edge. So I have 2 edges, right? 2 nodes, right? 0 and a. So I will create a link between 0 and a. So now let me see what it will print. So I can remove this. So you can see that graph with 2 nodes and 1 edges, right? So of course, printing is not a good idea, right? Printing is okay, but when I create this graph in your mind, it will be a figure. So maybe you want to see how the graph look like. So just another one more line, it will just to draw the graph. So nx.draw g. That's all. nx.draw g. You can see that the graph is the graph is actually drawn, but you can see there are some issues, right? Which is 0 and which is a in this, you don't know. So there are some uh, with labels. There is an option. Just give it true. Then if you run again, you can see that, yeah, this is a and this is 0 and it is connected with a link. Yeah. Now you created your graph. You can give the color maybe. The blue color may not be a good one, so maybe I can give violet. So let's see. Yep, so it's clear, right? So is that clear? Any doubt in this?
Yes, sir, clear, sir.
Okay, so this is not efficient, right? If you have millions of nodes, what you will do? You cannot write add node million times, right? You cannot do. So we can see how we can do that in a single line or something. If you have multiple edges, but I can tell you one more thing. you don't even want to add a node. If you simply add an edge, right? If you simply add an edge, the nodes will be automatically added. So see, I just rerun this. I just added an edge, because from the edge it will automatically take the nodes. That's also one option. But in graphs, right? In graphs there are some isolated nodes, because there are some nodes that is not having any link connected. In that case, you need to add node separately. That's one of the important thing. If you simply add edge, that's also fine. For example, there is a node, for example, 3, and it's not having any, see, this is a graph, right? There is a link and 3 is kind of isolated. In that case, you need to add node. Otherwise, if you have edges, if it is a completely connected graph, you don't need, because connected graph means all the nodes are connected to one of the other nodes, right? Every nodes will have a path. So that's one thing. What I will do is I will just create a I already created a sample graph for this slide, and I can show you how easily you can add that. Maybe I will just insert the file, insert the image, then let me see. Yeah. Yeah, you can see a graph, right? This is a figure. This is just a figure I draw. So maybe I can create this graph using using NetworkX. So you can see that there are nodes. There are 6 nodes in this graph, and there are different edges. And you can see there are edges with weights, right? Edges are having weights. That's very important in network analysis. All the edges will have weights. By default, the weight of each edge is considered as 1. For example, in the previous graph that we drew, right, this one. In this one, this is the default weight is actually considered as 1. So, but that's not the real case. For example, in a Facebook network, right? Facebook network, maybe the users or the Facebook users will be considered as nodes, and if they are friends, they will be there will be a link between those 2 nodes, and maybe the weight of the edge can be the number of messages or the number of likes or something between the two friends. So in that case, it will be an integer or some other weight, right? So we need to do that. So we can create this sample graph using NetworkX. So as I told, this is I will first create a dump graph. So the graph is created. Then since it is a connected graph, maybe I can go ahead with the, so first I can create an edges list. So in this list, I can provide all the edges. 0, 1 is my first edge, right? And just give its weight 0, 1, 4. Okay, so it means that there is a link between 0 and 1, and its weight is 4. So like that, you can actually create tuples 0, then 3, then 1. That is the second edge. Then 0, then 4, then 2. That's the third edge. Then from 1, I will try to add 1, 2, then 5. Because I don't need to add this. So let me tell you one thing. If you simply create nx.graph, it is an undirected graph. There is no direction. Okay. If you want to create a directed graph, just to give digraph. That's enough. Just mentioning. So by default, graph is undirected. So I don't need to add 1, 0, because 0, 1 and 1, 0 are same. Then 1, 2 is 5. Then from 1 only that. Then from 2 I will start to add 2, 3. It's 3. Then 2, from 2 there is a 5. It is 2. Then from 2 all are added, right? Then 2, 5, 2, 3. Then from 3 I will add 3, 4. It's 2. Then 4, 5. It's 1. Right. So how many edges we have? 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6. Yeah. So I just created a list of edges. Okay, so that I can add all the edges with weights in a stretch. So what I need to do is now So I have a dump graph here, right? So to this graph, I need to add all these edges. So what you need to do is just to do, so add weighted edges from. Okay, it's like you are saying English. Add weighted edges from. Then which is the list that is providing all the edges. So just give edges. Okay, that's all. So now your graph will be created. So we'll see how the graph is looking like, right? nx.draw, then g sample, then width labels equal to true, maybe not color, I'll give orange. So let's see how it, see the graph is created, but something is missing, right? the edge weights are missing, right? So that we will draw the edge weight. It may not look like this. Maybe the orientation will be different, because in graph theory, the even though the look doesn't matter, but the look matters sometimes. So this is the same thing, but you can see that the edge weights are not labeled. So I don't know why, but in NetworkX, the drawing of graphs with edge labels are a bit tricky. A bit tricky means by default it will not draw the edge labels, means edge weights. So we need to do we need to add 2-3 more lines for that. First we need to draw the graph, then we need to draw the edge weight separately. So how we will do is something like this. First we need to find some position of the nodes. So for that, actually there are some layouts, like circular layout is there. Circular layout means it will try to arrange all the nodes in a circular fashion. Then there is spring layout, there is some random layout and all those stuff. So for this session, maybe I will use a spring layout. So first I need to find out the position. Position means spring layout I will use layout. Then I need to give G sample. So this will ultimately create some positions for the nodes. Maybe I can print and see whether it will print. Let me see. Yeah, you can see the positions for 0. The position of the in the coordinate system, right? The position is arranged like this. You can see the coordinates, but we are not going to use any coordinates as such. We'll use that position to put the nodes in a proper place. Now what I need to do is yeah, I need to draw the graph, right? I can draw the graph now. So it's in a spring layout now. Maybe G sample. Here I can give the position. So then with labels true is not required. I think by default it will do that. Let me see. No. Then what we need to do is actually maybe with labels I will put with labels equal to true. So it's giving the labels. Now we need to as I told, we need to separately draw the edge weights. We need to separately. So we need to take the edge weights from the graph. So how to take edge weights? So edge weights, how you can take is something like this. nx.get edge attributes. So edge weight is actually an edge attributes. Then what you can do is G sample, then just give weight. So it means that it will take all the weights from this graph from G sample. Now what we are going to do is we are actually drawing this weight on the edges. So it's a bit tricky. So let's see how it is. So nx.draw network edge labels. So you can see draw network edge labels. So we need to separately draw. So I'll put G sample. Then I need to put position. Position is we already did, right? Position. Then edge labels equal to. So you need to provide the edge labels as this edge weights. So maybe I can provide this. Okay. So let's see how it is. Oh, there is an error. Pro network edge labels. Okay, it's not network, it's NetworkX. Yeah. So now it looks like our graph, right? You can see that 0, 1, 0, 1 is connected with 4 as the edge weight. Then just to verify whether it is correct, whatever you give here, 0, 3, it's 1, then 0, 4, it's 2, then 3, 4 is 2 here, then 4, 5 is 1, then 3, 2 is 3. So 0, 1, 0, 1 we already checked, then 1, 2 is 5. So 1, 2 is 5. Yeah. So is it clear how to create a graph and how to draw the graph? Any doubts in this? This is required primarily. This is required to create a graph and see the graph so that you can check whether the initial graph creation is fine or is it in the correct manner. So any doubts now?
Sir, can we change the shape of the graph?
Of course, yes. Maybe we can try a circular layout. These are actually inbuilt algorithms, and you can change that. Yeah, it is. I will not say it will be always circular. The thing is that it will try to orient in circular fashion. So it's all our inbuilt algorithms. One more thing I can tell you. If you want to fix the positions of node in a specific place, this position you can write a separate your positions in a simple list and you can draw. Okay, ultimately what happens, this position is actually a list. It's a dictionary, right? You can see that the 0 will be actually positioned at this coordinate. The node 1 is actually positioned at this coordinate. So you can write this, right? Manually you can write if you want to place the nodes in a fixed position and just draw it. So it will be at that particular position. Yeah. Is that clear? Let me try random. Yeah. There are different layouts available. You can just check and just try something to make your graph clear to others. That's all. Yeah, Spring is.
Yes, sir. Thank you, sir.
Let me try spectral. There is spectral layout also. No, it's not spectral. Oh, I did a spelling mistake. Yeah, this may be much better. Yeah, if you can show your graph in a planar fashion, that will be much better. Yeah. So is that clear? Any more questions? Okay, if not, we can just go through some of the basic things, basic algorithms that we can do with the graph. So one of the primary things that we do with the graph is finding out the shortest paths, right? Shortest path between the nodes. So we can see whether we can do some shortest path between the nodes. So I will just comment this for now. So that we can just look at this graph and see. And first, there are different things. Okay, if you want to find out the degree of a node, there is some function like degree. For example, we can see. So d equal to degree, then degree of 3 we can find out, right? Degree of 3 is actually 3. Let's see whether it will happen. Print d. So yeah. Oh, it's 0. Oh, it's not G, right? It's G sample. Okay. Yeah, it's 3. So you can find out degree like this. Then if you want to find out the neighbors of 3, That's also is possible. Maybe I'll put it like this: g sample dot neighbors of 3. I need to make it as a list here. I need to convert it as a list. Then maybe we'll see whether it will print the neighbors. So yeah, you can see that. So this is the degree. This is the neighbors. You can see that 0, then 2 and 4. This is the neighbors. These are some of the fundamental things that you can do. There are a lot of functions to do that. Then we can focus on the shortest path and path length. That will be very important for your course. So let us see how we should do that. So as an example, we will try to find out the shortest path between 2 and 4. Okay. So what we can do is maybe let me make a variable. So the function that is used is shortest path. Okay, shortest path. Then what you should do is you need to give the graph, then 2 and 4. So let's see what is the path. So I'll just print the path. Okay, print path 2, 4. Okay, so let's see. So path from 2 to 4, right? The shortest path is 2, 3, 4. 2, 3, 4. Is it the right? Is it the shortest path? Do you think that is the shortest path? 2 to 4 is 2, 3, 4 or 2, 5, 4? So it is 2, 5. Yeah, but why it's short 2, 3, 4? Because as I told, by default it will take the edge weights as 1. Okay, edge weight as 1. So if you consider, if you just ignore all these edge weight, this is 2 hop path and this is also 2 hop path, right? So that's why it took one of the 2 hop path. So if you want to use the this is very important, because lots when we code the our analysis, right, our algorithm, we used to forget this, and this may create wrong results actually. So for using the weight, you need to give something like this. So weight equal to, so our parameter is actually weight itself by default. So it's called an edge attribute. Its name is edge itself, weight itself. So if you want to use this weight, you need to give something like this. So now if I run it again, you can see that the path got changed to 254. Okay, so you should not forget this. By default, it is always 1. So sometimes I used to make these mistakes every time, and we will not get the expected result, right? So this is very important. So if you want only the path length, then maybe you can use nx dot shortest path length. Okay, so same thing, just to give the same parameters. Okay, so I can print path length. So it will give the path length. It's 3. Okay, this is shortest path length. So this is between this is actually between one source and one destination, right? So we will try to see how to find out path between all sources and destinations. So if you want to see all pair shortest path, right? So then maybe I can show you all pair paths to ns dot shortest path. Just to give your graph, that's enough. You don't need to specify the source and destination. Then it will give all pair. So print all pair paths. Let's see. See. So this will give between all pairs of nodes. So how to interpret this? So this is a dictionary. That's why I told you that you need to be very familiar with the dictionary data structure in Python. So you can see that from node 0 to 0, the path is 0, right? Then from 0 to destination 1, the path is 0, 1. Then from 0 to destination 3, path is 0, 3. So from 0 to destination 2, the path is 0, 1, 2. So it's in that way you can interpret. Okay, so One more thing I will tell in terms of the path length, that is the average path length, that is called APL. That's very important measure in complex network analysis. So if you want to see the average path length is nothing but you take all the shortest path length between all the pairs and just average it. That's average path length. It's called APL, right? So how to calculate APL? I made a mistake here, right? Here I need to give weight equal to weight. Otherwise it will show the okay. Otherwise it will show the shortest path with weight as 1. So yeah, now we will calculate APL. So APL, how to calculate is there is average shortest path length G sample. Yeah, same thing. Just give, then print maybe APL. Yeah. So let's see. Yeah. So the APL of this graph is actually 3.4. Okay. So just a single line. So it will compute the APL. Okay. So any doubt in average path length and path length? This is very important. This may be the fundamental thing, fundamental metric that you use to measure some characteristics of your graph. Any doubts in this portion?
Oh, sir.
Okay. So some of the other metrics that I can mention you that's actually related to your course is called centrality measures. There are different kinds of centrality metrics. One is called closeness centrality. Closeness centrality actually measures for to each node. Each node is how much close towards from other nodes in the network, right? That's one of the important thing in complex network analysis. For example, in city planning, I can give one case study, right? If you have a big city and if you want to build a hospital, so what is the thing that will determine the position of hospital, right? So the important thing is the hospital should be reachable within minimum time from all the locations in the city, right? So in that case, what we used to do is we will create the road network of the graph, the graph of the road network, and we will find out which actually which node is having the most optimal closeness centrality. So we will build the hospital near that place so that everybody can reach to the hospital within minimum time. So that's one of the applications. So that's the application of closeness centrality. Then there is betweenness centrality. Betweenness centrality actually measures how a particular node is taking part in the shortest path between other nodes. So that's betweenness centrality. So I can just give you two measures, closeness centrality and betweenness centrality for this session. So remaining you can explore. So to find out the closeness centrality, what you need to do is just it's the functions are just similar to this. So what you need to do is nx dot, there is a function called closeness centrality. Just go there, then just give the sample. Then what you need to do is, so instead of weight, here you should give the parameter called distance. Distance is our weight measure, that's all. So closeness. So if you do this, you can see the closeness centrality of all the nodes. So for the node 0, the closeness centrality is like this. 1, it is closeness centrality is 0.1, 3 closeness centrality is 0.3. So you can get this. This is the closeness centrality metric. Then if you want to do the betweenness centrality, nx dot betweenness, just give betweenness centrality again. Sample distance is weight. You can see betweenness. So if you do this, made a mistake. Between. Sample. Oh, it's not. It's not distance. No, it's actually weight only. It's not distance. In betweenness, it's different. Yeah. Closeness, it's distance, and for betweenness, it's weight. Yeah. So you can get the betweenness centrality for all the nodes here. Then if you want to get a particular node, just give. If you want only 3, betweenness centrality of 3, just give this. So you can give 0.1 because it's a dictionary, right? So just give the key value as the node, then it will provide you the betweenness centrality of a particular node. In fact, here also you can give, if you want betweenness centrality of only 3, it's optional actually. So you can get here only for 3. Sometimes, mostly you will go for finding out the average betweenness centrality. So for closeness centrality, then in that case you need to get the centrality measures of all the nodes so that you can be average. It can be average. Yeah, that's just 2 measures for closeness and betweenness. You can just go to that tutorial that I mentioned. You can see different centrality measures like degree centrality, then eigenvector centrality, and all those stuff. Any doubts in this? So giving weight is actually very important. Is that fine?
Yes, sir. Yeah, I think that's fine. Yeah.
Okay. Yeah. So now maybe one more important metric I can provide that's related to the capacity of the network. It's called flow. Flow capacity you can say. So it's important to find out in some cases what is the maximum flow, maximum amount of data that you can transfer from one node to another. So it's very important in modeling, for example, the water pipeline network or electricity network or even road network. You can where the edges will be labeled with the flow, maximum flow volume of whatever it is going through a node, going from one node to another, right? In that case, the maximum flow in a graph is of important influence to analyze. So there is also there are functions to find out the flow of the graph. So maybe we can see the flow of the graph in this graph itself. You can see, right? So whatever I am sending from 0 to 5, for example, how much flow is allowed from 0 to 5. From this graph itself, you can understand that what can be the maximum flow. It is 3, right? Because to 5 at a time, it can maximum get 3 units of 3 units of data, because this is its incoming edges are like 3. Even though from 0 I can maximum how much I can give the flow. It's 4 plus 1 plus 2, right? 7 units of data I can even transmit from 0, but 5 can receive at the same time only 3. So maximum flow to 5 is always 3. So we can just see whether we can get that result from the NetworkX library. So I'll try to show the flow value. So there is a function called maximum flow value. So maximum flow value. So here you should give as usually you should give the graph. Then you should give the source and destination. So 0 to 5 I will give. Then you should give the weight. Assume that this weight is representing the flow. Means from 1 to 2, the maximum flow is 5. Assume that this weight is actually flow. Then we need to give that as well. By default, as I told, it will take 1 as the flow, but here we need to give the flow. So for giving the flow, which attribute is representing the flow, you need to give a parameter for capacity. So in our case, I am giving capacity as our weight itself. Then we can see what is the maximum flow that is possible. Yeah, so it's 3. Okay, so whatever we analyze, right, it's 3. Oh, let me reload the page. Somehow it got Let me restart the. Yeah, flow, right? So if you want to see the flow through the edges in this particular flow, there is actually, if you just remove the this value from this, right? So this will actually give the flow and the flow edges also. It will give two values actually. This maximum flow function. This is maximum flow value function. It will give only the value of the flow, but maximum flow will give the flow through each edge also from 0 to 5. So maybe I can print this, print flow and flow edges. So let's see. Oh, I need to rerun again. Yeah, you can see here. So the maximum flow is 3. And you can see that from 0, 1, the edge in edge 0, 1, it can be 4. Then 0, 3, edge 0, 3, there is no flow. Then 0, 4, it is 0. Then 1, 0, it is 0. Then 1, 2, the edge 1, 2, it is 4. So like that, you can see in all the edge what will be the flow value in all the edges. So that's one function that's giving both. If you want to analyze the individual flow at individual edges, then you need to do with this function as well. Then that's one of the important thing. Then you might have heard about the max flow min cut theorem, right? The maximum flow in a graph is same as the minimum cut in the graph. So the minimum cut is ultimately the cut that separates between the source and destination with minimum weights, right? So maybe we can verify that with the there is another function called cut, minimum cut also. So nx dot minimum cut, then you give the same thing, the same arguments, and we can just print the cut. So that also should give 3, right? Yeah, you will get 3, right? 3 is the value, and in addition you will get the cut also. So if you cut this, right, what is the cut in this graph? So cut is actually this one, these two edges. So when you cut this graph like this, you will get a subgraph 5 alone, and the remaining will be another subgraph. So you can see here. So see, you can get the subgraph from here, the cut from this function. So that's also very important. Yeah, is that clear? This is kind of analyzing the graph using centrality measures and average path length and all those stuff. Is it clear? Any doubts in this?
Sir, this cut one, can you explain again? The internet was gone.
Oh, internet is gone.
Yes, sir. This cut one, sir.
Oh, okay. So you heard about min cut, max flow min cut theorem?
They have not studied that.
Okay, yeah. It's okay. Cut is actually the set of edges using which you can actually separate the nodes. For example, a cut between 0 and 5 means the set of edges. If you remove those edges, 0 and 5 will be separated. It will be disconnected. It will be disconnected. Okay, that's the meaning of a cut. It's a set of edges. By removing those edges, you will separate the source and means two nodes. So the 0 and 5, if I am giving the 0 is the source and 5 is the destination, then what is the minimum cut? So if you cut these three edges, right? For this edge 0, 1, 0, 3 and 0, 4, if you remove these edges, still 0 and 5 will be separated because there won't be any path towards 5. But the weight of this cut is actually 4 plus 1 plus 2, it's 7, right? There is another cuts. See, like this you can cut like this. So if you take all the cuts and check which is the minimum cut, so minimum cut will be ultimately this one. This, if I take these two edges, 2 and 1, it will be 3, right? So compared to all other cuts, so this cut will be the minimum. There is a theorem called max flow min cut theorem. So the maximum flow will be the minimum cut. Okay, so taking the maximum flow is same as taking the minimum cut. That's all. And that's called the minimum, the match flow min cut theorem. Is that clear?
Yes, sir. Got it, sir.
Yeah. So you will learn the proof probably in the course. So that's all about analyzing graph. You can go through different functions. Even there are different centrality functions and different arguments you can provide. So we have 10 more minutes. So I will just go through creating some interesting graphs. Then with one more thing, maybe we can finish the session. So you know, right? Complex network means it's a network with millions of nodes, right? And millions of nodes, they are having different properties. For example, maybe you might have studied small world property, then scaling property, and all those stuff. So there are different types of graphs that in literature that are actually showing different kinds of properties. So I will the NetworkX is already providing some of the functions to generate such graphs with the different parameters. Maybe one of the graph that you might have studied is called Erdos-Renyi graph. It's a random graph where you can there if you are giving n nodes, for example, you have 10 nodes, the edge you need to provide a probability also along with the nodes. What that probability represents is for each pair of nodes, an edge is actually created with that particular probability. For example, if you have n nodes and probability is p, it means that there will be n nodes and an edge will be connected between two nodes is with probability p. Okay, so that's the idea. So it's called ER graph in general. So I'll tell you how to create an ER graph. So I will create GER. So there is a function called Erdos-Renyi graph. Okay, just give the number of nodes you want and the probability. So I will give the probability as 0.1. Okay, the graph is created. Okay, just one line with 100 nodes, the graph is created, and the edges will be added with probability 0.1. So just see how this graph look like. Draw, right? Draw GER maybe with labels true, node color violet. Yeah, let's see how it look like. See, an ER graph is actually created. So if you want to see, so you can see the links are connected. Maybe we can reduce the probability to 0.05 and see. Yeah, you can see there are no much edges. Maybe I'll make it 0.2. Then the number of edges will be less. Yeah, it's disconnected. If you give 0.5, then it will be more edges. See, just 100 nodes. Each two nodes will be connected with an edge with the probability 0.5. So more the probability, there will be more edges. That's all. So 0.5 will look better, right? So most of the graphs may be having this kind of characteristics from the popular data sets. So this is one. Erdos-Renyi graph is one. Then there is another graph called Watt-Strogatz. Watt-Strogatz graph is something. It's work on the basis of rewiring. So first you will create a circular graph, then you will remove one edge from the circle and you will try to rewire that edge to some other node. So I will just create a sample Watt-Strogatz graph also. So you can see that ns dot Watt-Strogatz graph. Then in this you need to give the number of nodes first. Then you need to give in the circle. I told you, right? In the first place, it will try to create a circle. The algorithm will work like this. It will create a circular kind of graph, a cycle. So the 3 is for each node should be connected to how many nodes around it. So it's 3 nodes I just provided. Then what is the chance of rewiring? That's again a probability that you should give. So let's see. Let's see how it is. Maybe I can copy the code from here. So I need to just yeah. Yeah. Let's draw it again. You can see some rewiring here. Yeah, see the graph. So first it will try to create a cycle, then it will try to rewire it using the probability 0.5. So it's called Watt-Strogatz graph. And another important graph is called Barabasi-Albert graph. This is also important. This will be in your syllabus. So I will create that graph also. It's called Barabasi-Albert graph. So as usual, you should give the number of nodes first. Then what is the next argument? In Barabasi-Albert model, the next argument is each node is joining to a network and it will connect to some k number of neighbors. It will tries to connect to k number of neighbors. Okay. For example, it's like this. If you are in a scale-free network or Barabasi-Albert model, if you are joining in a particular network, assume that you are joining in Facebook. You are signing up in Facebook. So you will try to have maybe some try to connect some four number of nodes kind of thing. So each node added to the network is trying to connect to the node with highest degree, of course, because you will try to be friend with the most popular person, right? So there is a higher chance of joining you a node with another person with high degree, it's called. So I just give 4 as a value. So the first node, a node that is newly joining, it will be try to connect with another 4-degree node. Then maybe let me see how it will look like. Let me run this. Yeah. So this is a Barabasi-Albert model. Okay. So you can see that most probably it will be the nodes will be connected to 4 nodes. You can see a lot of 4-degree nodes in this. So these are just 3 different graph models, already existing graph generators. You can try with, and you can experiment with the different number of nodes and probabilities and all those stuff. Any doubt in this or any questions?
No, sir.
Okay. So let me close it and open again. Yeah. Okay, so maybe the last item I can provide you is so now actually we created the graphs using manually providing the edges and or using the graph generators, right? And this is not the case always. What you used to do is you need to download some data set from some of the uh, public URLs, right? For example, you have a very large data set in Stanford library, uh, complex network data set. So you will usually get the data set in the form of a file, like a comma separated value file or something. Maybe I can give you an example, right? So you will get something like this, a file something like this. So you need to create the graph from this file actually. Okay, that's always, that will be always the case. So this is actually representing there is an edge from 1 to 2 with weight 10, 2 to 3 with weight 20, 1 to 3 with weight 4, so like that. So how to create a graph from a file? So that's also very important for your network analysis. So that's also very easy. Just one line of code in Python, of course. So I'll create a graph from that. Okay, from that file. Maybe I will create a G data. So there is actually a function called read weighted edge list. Okay. So if you are writing if you are writing the edges, so this is ultimately listing of edges, right? Listing of edges in a graph. So it's called edge list, but it is having weight also. In some cases, unweighted graphs, there will be only these two, 1, 2, 2, 3, like that. There won't be any weight. It's called unweighted graph. So ultimately it's called an edge list. So this, since it is weighted, the function is called read weighted edge list. Then what you need to give is, you need to give the file name. So my file name is, I think, CSV, right? What's my file name? Yeah, sample.csv. Then what you need to give is, you need to give the delimiter. Delimiter is actually what is separating these two, right? Each column. It's actually comma, right? By default, I think it's space. So you need to give delimiter here. That's all. Nothing else. One line, you created the graph from the file. So then let's draw the graph and see whether it's correct. I will just copy paste the code. Yeah, this is the code, right? We'll see. We'll try to. So I will find out the position. Then it's G data. Then edge weights will be data. Then yeah. So we'll try to see how it look like. Yeah. So this is the graph, right? This is the graph I loaded from the file. Let's look. We can verify, right? So 1 to 2. Yeah, there's an edge with weight 10. Then 2 to 3. Yeah, 2 to 3 there is 20. Then 1 to 3 it is 4. Then 2 to 4 it is 30. Then 4 to 5 it is 10. Then 2 to 6 is 20. Yeah, that's all. So this is one way to read the graph from the file. And if you want to write the existing graph to a file, for example, you will write some algorithm to find out rewiring of your graphs and all those stuff, and you want to reuse the graph at a later point of time, then in that case you can save the graph in a file, right? So if you want to save the graph in a file, there is a function called write edge list. So this is read edge list, then write edge list, and write weighted edge list. So maybe I created a graph here, right? It's not from a file, it's actually using a function. For example, I want to write this graph to a file, this Barabasi-Albert graph to a file. So how I can do is, maybe I will do it here itself. So nx dot write edge list. Since it's not weighted, I am not using write weighted edge list. So GBA, that's the first argument. Then just give a file name. For example, BA graph.csv. Then if you want to use a delimiter, then just give the delimiter. Okay, if I run this code, yeah, let me go and see the BA graph, right? Yeah. See, you can see the edge list. This is the edge list. And the last thing is, actually there are there is no data, right? There is no weight. That's why by default it printed a dictionary here, an empty dictionary. Maybe you can actually remove that as well. If you are giving data equal to none, then what happens is oh, it's not data equal to none. Okay, it's not none, it's actually false. So there is no data, right? So if you go there and just look at it again, you can see, oh, I did not run it again. Right, it's BA graph, right? Yeah, so it's gone. Now it is simple unweighted edge list. Yeah, so I think from my experience, these functions are enough for you to start with NetworkX, and mainly to read data from file and writing data to file for your later use. Then especially in complex network analysis, you need to go with the Barabasi-Albert model, then Watts-Rogarts and Erdos-Renyi model, random graphs, then centrality analysis, then capacity analysis, average path length analysis. And these steps are the most critical thing in any network analysis. So you can model any real world network kind of this, and you can try for analyzing whether it's actually possessing some of these properties of random graphs, and do the analysis. And yeah, one more thing maybe. If you want to, now the figure is here, right? If you want to save the figure as a file, right, you can do save fig. Let me see, I forgot actually. ba.png. Let me see whether it will work. Oh, save fig. Oh, I forgot. Oh. Oh, it's not save it. Actually, for saving the figure, because if you are writing a research paper, right, you need to you actually need to save the figure in a PNG or PDF format. That's why I told you that you need to install one more library called matplotlib. So we need to actually use the matplotlib library, and you need to import this library as PLT. So it's kind of thing. This is pyplot. It's using a Python plot function for plotting. So then we need to use this one to save the figure. For example, we can save the it's plt.save figure. Let's see whether it's correct. Yeah, plt.save fig. We can see whether ba.png is there or not. It's not again. Maybe I need to restart everything. Yeah, I think it is run. Then let me go and see. Yeah, you can see a PNG picture like this. So this you can use to include it in your research paper or something if you want to save the figure to do the presentations and all those stuff. So I think I took 10 more minutes. So any doubts? I will stop here because this is enough to start with the NetworkX. And yeah, if you have any questions, just feel free to ask.
Any questions you can ask now?
Any questions related to plotting analysis or something?
Sir?
Yep.
Hello, sir. Yeah,
Yeah.
sir, how exactly is it practically possible to use this tool to draw a million number of nodes to draw very large data, like having
Yeah.
more than million number of nodes? This
Yes.
looks not possible to through this tool.
It is possible to draw, maybe there will be more number of nodes, and there will be more cluttered nodes, right? That's what your concern is, I think. So you can reduce the number of you can reduce this node, its radius, right? You can reduce the radius to very small value. If you know the million, the if there is a graph with millions of nodes, right? You don't want to see each node with a label, right? You may want to see the node that may be having the more number of connections and all. So there are techniques to enlarge the node that are having specific attribute. For example, you can make only the node with higher degree, or you can adjust the radius according to the degree of a node. That's possible. Okay. So it doesn't matter that so other nodes will be just a small point or something. You don't need to see all the nodes with a big circle. Only some nodes with a higher number of nodes. Maybe let me see whether quickly we can find out some complex networks. Maybe if you go to image, you can see if you look at this graph, right? See, this is also a graph. If you look at this is also a graph, but you will not see all the nodes in a very big circle. It's kind of some nodes with some specific values. This graph actually works perfect. Yeah. So see, maybe some of the nodes here, right? These are having higher degree. That will be projected as the nodes with a big drawn with a big radius or something. So other nodes will be very small ones. See, usually people are interested in these patterns, more interested in these patterns, and you can draw this like this in NetworkX. But from my experience, I can tell you drawing graphs. I told right the iGraph is giving more interesting functions to draw the graph. So sometimes I use NetworkX to do the analysis and iGraph to draw the graphs. Yeah, but it's your choice, right? Network is also is good to draw the graphs with the layout. That's also a good thing. Yeah. Is that answer your question?
Yes, sir. Thank you.
Okay. Yeah.
Sir, and previously you have mentioned about loading a road network data and analyzing the point for locating the hospital.
Yeah, correct.
So, how exactly is that done in this tool? I didn't get that.
Oh,
How do
okay.
you analyze that?
Oh, okay. So that's one of my paper. Maybe you can read the paper. I can tell you just simply see road
Okay.
network is a graph, right? Road
Yes,
network
sir.
can be represented as a graph where the junctions will be nodes and the roads connecting junctions will be edges, right? Then the edge weight will be the
Yes.
distance of that road, right? Then in that, then you just find out the closeness centrality of all the junctions. Is it clear?
Yes, sir. Yes, sir.
Yeah, you just create a graph using road network, then give the weight as the length of the road, then find just to use the function closeness centrality, and then you can understand that which node is having the lowest closeness centrality. I think the minimum closeness centrality. That node is, what is the meaning of
Okay.
minimum closeness centrality? It's what is the physical meaning of that? That node is the most closest to all other nodes in the network, right? So that's the physical meaning. So you just build the hospital nearby that junction. That's enough. It means that that's where we are actually converting our code to a real application, right? Is that clear?
Okay. And sir, is there like any data set can be created using this tool, given inputs?
Yes,
Like
yes, yes.
taking a road network as an example, giving it a is it possible to create a road network data using this tool?
Yeah, of course, yes. In fact, we have a lot of work in that aspect. You know, there is actually there is a website called OpenStreetMap. It's similar to Google Map, but it's actually an open source version like Wikipedia, open source version of the Google Map, you can say. So where I am now, maybe I can see the road network right from here. So this is the road network where I am currently now. So if you go to export, you can see that in when I joined for PhD, one student, one undergraduate student, he was working giving data to this OpenStreetMap for the Dharavi place Dharavi in Mumbai, right? So they added the road coordinates and all those stuff to this OpenStreetMap. Okay, so what we did is we did a lot of analysis using this. So if you can export, you can export a road network like this. Okay, you can export like this. So if you export, you can download a file. Okay, this file is an XML file ultimately. Oh, I need to open it. Let me see. Downloads. Oh, yeah, map.osm. Let me open it with. Yeah, you can get an XML version of the all road network coordinates using this. Maybe you need to do some text processing in Python. Using this, you can actually create a road network graph. Okay, so you can see a particular. This is actually a junction. This is representing a node. You can see a node. This is representing a junction, and see highway. This is a highway, and then there are a lot of attributes. If you just, this is very easy to understand, and if you analyze that, you can just create a road network from this, and you can create a data set your own. Yeah, if you want, I can.
Yes,
I
sir,
think
got
I
it.
have the code to do that because I developed code for doing that. That from the OpenStreetMap thing, you can actually create the graph and analyze. Yeah, if you want city road network graph, I can provide it because I did a lot of analysis using
Sure,
road
sir.
networks. Yeah, yeah. Just send me a
Yes,
mail.
sir.
So
Thank you so much. That would be really helpful.
yeah, yeah. Just send me a mail. Maybe.
Yeah, sure, sir. I'll definitely.
So here is my mail ID if you want to take. Yeah, any more questions? It's very interesting to analyze graphs because one of my friend who did PhD in graph theory, right? Yeah, he told that why he choose graph theory is there is no prerequisite. Means anybody can do graph theory. That's why it's actually in social network, in psychology, in neural network, in brain science and everything. It's graphs and complex networks. So it's a very diverse and interdisciplinary thing you can analyze. It's so interesting. Yeah. Any more questions or suggestions or anything you want to get from me?
Any further
Hello.
questions from anybody?
Hello.
Yep.
Thank you for the session, sir.
Uh-huh.
Sir, can you share this notebook, sir?
Can you repeat?
Am I audible, sir?
Somehow your voice is not clear.
Okay, sir. I'll type it.
Okay, you just want to share the notes?
Yes, sir. Can you share these Jupyter notebooks, sir?
Yeah, I'll
If
share
possible.
you. Yeah, I'll share.
So
Thank you, sir.
thank
Thank you
you
for
for
the session.
taking out time for us from your schedule and scheduling this session for us.
Yeah, no problem. Yeah. It was actually difficult to provide a talk in 40 minutes, 50 minutes because it's a vast topic, and I just covered something that is very important for you for the course. You can start with this and just go through the tutorial. You can explore whatever. There are functions for everything, so just you don't need to do much effort in coding and making your analysis. Yeah.
Thanks, sir. We'll do that.
Mm-hmm.
Okay, then if there are no further questions, we can thank the speaker, Dr. Sharat Babu, for his time that he has spent for us. So thank you so much, Sharat, on behalf of all students with me. Thank you. So this training that you have given will be really valuable for them to start analyzing the graphs.